So, yeah, I should say that everything in this talk is joint with Cyril Lecuyer. So, right. So I'll talk about iteration on Schottky space towards the end of the talk. But I think in order to sufficiently motivate it, I have to I have to spend some time discussing some other work. So, all right. So let's fix M, a compact 3 manifold, hyperbolizable. So 3 manifold with boundary. Here's a picture of said M. Okay. Of course, all 3 manifolds have genus 2 bound. Well, okay, fine. So here's a picture of your M, and so our interest today is in hyperbolic structures on the interior of M. So just for this preliminary exposition, let's set H of M to be so the set of all complete hyperbolic metrics on the interior of M. And let's consider them up to isometry, isotopic to the identity. Okay, so so this is a Teichmuller space, if you will, of hyperbolic metrics on the interior of this 3 manifold. So, okay, and if you like, you could topologize this by saying, okay, when are two hyperbolic metrics close? Well, they're close if they're like C infinity close on compact subsets of M, if you like, and then one can take the quotient topology. Okay, so then this is a space of complete hyperbolic metrics on the interior of M. So inside of this space, we have a distinguished subset. I guess I'll call it QH of M in this talk. So this consists of all the convex co-compact hyperbolic metrics. Right. So the picture here is, well, okay, maybe here's your 3 manifold that has 2 boundary components, and then if I want to draw a convex co-compact metrics on the interior, then the geometric picture is that so there's this compact convex core. Okay, so this is a compact submanifold where the complementary components are these product neighborhoods of the boundary of M. And here the metric in on the ends is exponentially expanding, if you will. So, right. And so what do we? I guess maybe why Q instead of C or something? Well, so in the case that M is a surface across an interval, then so this is what's called Quasi-Fuchsian space, and the Q comes from that. So just one remark. So this QH of M is open and dense in H of M, where the density here is from the Beers-Sullivan-Thurston density conjecture proved by Namazi Soto. Okay, so we'll primarily be interested in these convex co-compact metrics on the interior of M. And so how do you think of them? Well, so there's a parameterization of QH due to Alfor's Beers which says that so there's a homeomorphism from the homeomorphism, and Q goes from the Teichmuller space of the boundary of M. Okay, so remember the boundary of M may be disconnected here, so this means a product of all the Teichmuller spaces of the boundary components. And it goes to QH of M. Okay. So, right, and so what is the point behind this is somehow that, if I take one of the ends of my manifold, and then, I could look at sort of level surfaces as I go out this end, and so the metrics, the metrics are being exponentially distorted, so they're exponentially expanding. But somehow, if I just look at them conformally, then they're limiting to this conformal structure at infinity, which is the coordinate in Teichmuller space corresponding to this manifold. Okay. Right. And so for each one of the ends, you get a conformal structure in infinity, which gives you this this point in the product. Okay, so then the very very the very very big problem is so given a sequence in QH of M, so describe its geometric limits. Okay, so part of what's what goes into this question is, well, okay, I said that this was an open and dense subset in H of M. So so these convex cocompact metrics can limit to other hyperbolic metrics on the interior of M that are not convex cocompact. Okay, so that's this is included in this question, but also more can happen. So in fact, like if you take a sequence, so certain sequences of convex cocompact metrics here limit. Well, there's some sort of like fracturing in the limit in which so instead of recovering another metric on the interior of M, you actually recover a hyperbolic metric on some other manifold. And so maybe to state this a little bit more precisely, well, okay, I'll say it vaguely right here. So I'll say, so these geometric limits that I'm talking about, well, there are hyperbolic 3 manifolds, but maybe not homeomorphic to interior of M. Okay, so let me say a little bit more precisely what I mean by geometric limit here. So definition. So we say that so a pointed a sequence of pointed manifolds. So let's just say they're hyperbolic manifolds. So Ni Pi converges geometrically to a pointed manifold NP if what? Well, if there exists 1 plus like epsilon I by Lipschitz embeddings. Let's move over here. well, so if there exist these almost isometric embeddings from large balls in the limit into the approximates. So there exists 1 plus epsilon I by Lipschitz embeddings like phi I from B. So a ball in M around the base or in N around the base point P of radius Ri into Ni, sending P to Pi with so Ri going to infinity and epsilon I going to 0. Okay, so, right. So what are we saying? Well, okay, so we're saying basically that the metric, if I pick a large ball in N around the base point, then metrically it looks very much like something that's, well, almost a large ball in Ni around the base point. Okay. All right, so so I mentioned that that if you have a sequence of hyperbolic metrics, in QH of M, then there can be this fracturing in the limit, where the limit does not have the topology of the interior of M anymore. So, I mean, one can see that this fracturing like very explicitly in 2 dimensions. So here, so let's take some hyperbolic surfaces. Okay, so, and what I want to do is I want to pinch this curve. So pinch this separating curve here, and then, okay, so the length of this collar goes to infinity. And so here are these are my manifolds Ni. And so if I take my base point Pi to be like over here somewhere, then what happens? Well, in the limit, you recover so a surface with a cusp. Okay. All right, because if I take a large ball around the base point here, then you see almost isometrically that same large ball in this in the approximating surfaces. Okay, so right, so let's get back to 3 manifolds then. So maybe for a first example, I'd like to talk about so iteration and a bare slice. So this will be and then after this we'll do iteration in Schottky space as promised. Okay, so let's set. So we had our compact 3 manifold. Let's set M to be equal to surface cross 0, 1. Okay. And our sequence of quasi-Fuchsian manifolds, so of convex co-compact metrics on the interior, is Ni, which is so Q of say some fixed x, and then f to the I y, where so here x and y are fixed. So fixed points in the Teichmuller space of the surface. And f is a homeomorphism of S. Okay? Right, so the picture here is just, here I have my surface cross interval. So out at infinity here, I have this fixed point in the Teichmuller space of the surface, and then out at infinity here, I have, so I'm iterating I'm taking an orbit of f as my parameterization. Right, so what happens? Well, so the behavior of this sequence Qx f to the iy depends on the Nielsen-Thurston type of the map f. Okay, so let's split into cases, and all the different cases are due to different people. So the first case is, well, when f is a pseudo-Nosov map, and this I think I should attribute to maybe Thurston and also McMullen. So this example is written down in McMullen's renormalization book, but I just feel like I should say Thurston too. So what's the picture when f is a pseudo-Nosov map? Well, so in this setting, so what happens is that geometrically, so geometrically, the convex core of this three-manifold lengthens. So the length here goes to infinity as with I. So essentially, you're picking up sort of like for each iterate of f that you take, you're picking up an extra block of geometry in the middle of this manifold. And so so this convex core sort of expands with I. And then, so for example, if I take remember this is a pointed convergence, so I need base points. So let me take my base point here, so on this left convex core boundary. Then what's the picture? Well, so this limits to, so in this case it actually ends up being a hyperbolic metric on S cross 0, 1 again. But now instead of being convex cocompact, I've picked up this degenerate end. Okay, so this is very similar to the surface example in some sense, right? I mean, you're standing over here, the thing lengthens, and then you lose track of the other convex core boundary in the limit.
What does degenerate?
Yeah, so degenerate means there's a classification of ends of hyperbolic metrics on the interior of a compact manifold, and so either they're sort of exponentially expanding like this, or they have like linear volume growth, if you like, and so there's right. I mean, there are many definitions, but like this kind, the other kind of end is the degenerate kind. Yeah. What's that? Yeah, in this case, it's asymptotically periodic. So actually, maybe for another example, like remember the convergence depends on base points. If instead I'd actually put my base points right in the middle of the manifold, then what you'd see in the limit, well, you'd sort of lose both convex cocompacts end in the limit, and what you'll actually see is it's the infinite cyclic cover of a mapping torus corresponding to F. Okay. Yeah. So. Okay, so that's the pseudo-Nosov case. Any more questions? Yeah.
I don't know if this makes sense or not, but the picture that you draw all of them like the same, you mean that when you use geometry on these certain slices is kind of similar, or?
Bounded, yeah. I mean, all these surfaces that I'm drawing here have bounded diameter, for instance. Yeah. Right. It's sort of these degenerate ends. Well, okay. At least in this case, this degenerate end is like bounded diameter in the level surface direction, and then it right, and it goes. So. Okay, so that's the pseudo-Lossov case. So how about for the next case, let's take when f is a twist. Okay, and this is work of Kirchhoff and Thurston. Right, and so in this case, okay, here's my manifold. Okay, and so let's say that we're twisting. I'm gonna draw a level surface in the middle of the manifold, but I mean, let's say that we're twisting around this curve. It doesn't matter. Yeah. So, all right. So we'll twist. Well, okay. I'm drawing in the middle, but really we're taking x here, and then we're twisting the conformal boundary over here by that by a twist around that curve. And so what happens? Well, so as I goes to infinity, this curve. So the geodesic representative of the curve in the 3 manifold, the length of it shrinks to 0. Okay, so shrinks to 0. And well, okay, so maybe a more accurate picture of what's happening near the geodesic here. So let's take our magnifying glass in which we transfer between 2 schematic representations of 3 manifolds. So what happens is that, in the neighborhood of this curve, really what you're looking at is so it has a neighborhood that looks like a solid torus where the curve is like very short and way out here. Okay. And so in some sense, like you're seeing the similar picture that we did with the surface earlier. And so what does this limit to? Well, okay, and so then this solid torus lengthens in this direction, and so what happens is that in the limit you lose the curve. Okay, so the geodesic of the representative of the curve sort of goes to infinity, and you lose it in the limit, and so in the limit, what you see is topologically it's just a surface cross R, except I drill out the curve. Okay, so drill out. So if maybe this curve is gamma, I drill out like gamma across a half from S cross a half, if you want. Okay. And so that's the topology of the limit, and geometrically you've generated a cusp. Well, yeah, I mean, almost no matter what the base point is. I mean, so here I guess I'm taking take your base point like here. Here. I mean, the only way to get a different geometric limit is if you actually like take your base point here or something, and then, well, you're not going to get so you won't get a geometric limit in that case. It'll in some sense be converging to like to a line. And so there's some, but so unless you put your base point like right here, then all geometric limits will give you this manifold with the curve drilled out. Make sense? Okay. All right. So yeah. So maybe for the last example, so let's take the case now when f is a partial pseudo-Lossov. Okay, and so this is due to Brock. So this was Brock's thesis. And so what happens in this case? Well, okay, so let me draw the manifold again. Hmm?
Partial.
Yeah, partial means, where can I draw it? All right, so if this is S, so I want to do like a pseudo-Nosov on maybe this bottom part. Okay, so fx is a pseudo-Nosov on the bottom, and maybe is the identity up top. Okay? So, all right, so when f is a partial pseudo-Nosov, then, okay, what's the picture? Well, so here's our manifold. And then what happens is that as I goes to infinity, so as you start iterating this pseudo-Nosov on just the bottom half of the surface, then, well, you might expect something similar to happen to what's happening with the fully pseudo-Nosov example. Okay, so for each iteration of f, you sort of stick in a bunch of geometry to the manifold. And so yeah, something similar is happening here, except somehow you're only sticking in this new geometry to the like the bottom half of the manifold. And so, I mean, sort of what happens is that you end up developing this sort of abscess. Okay. Right. Yeah. Right. Okay. And so, right. So somehow iterating this partial pseudo-Nosov ends up, inserting, with like a syringe, all this geometry into this bottom part of the manifold here. And so then what happens in the limit? Okay, so in the limit, this then converges to the following, which is a little harder to draw than the previous ones, but that's okay. All right, so what happens is that, so topologically, in the limit, we just cut out a copy of this bottom part of the surface from one of the level surfaces. Okay, so it's exactly what happened in this, in like the Kirchhoff-Thurston examples. So here, like, all the map is really stuff. The map is happening on this curve here, and so in the limit, then we drill out the curve. So it's the same thing here. So your map is supported on this half of the surface, and so we end up like just slicing that out of the manifold in the limit. And then the picture is, well, okay, well, I guess I should draw it like this, and then let me draw another picture as well. Okay. This is starting to get a little graphic because in some sense, like, right, I have this abscess developing, and then in the limit, right? Yeah. But so what's the point here? So this manifold here is, so it's homeomorphic to S cross 0, 1 minus well, if this subsurface here is T minus T cross a half, and then but then geometrically, what happens is that you develop a geometric end for this manifold, sort of for each kind of on each side of the surface that you cut out. Okay.
The top half is a geometrically finite end with a cusp now.
So which? So here or the top half?
Yeah, that becomes
Um,
smaller.
Oh, you mean, yeah, if I take the cover corresponding to that? Yeah, right. Yeah. So I had these, right, so I still see the convex co-compact ends here, and then I developed these two sort of degenerate geometric ends down here.
So there's a new parabolic now?
There's a new parabolic that that joins these two geometric ends that you see here. Okay. So I mean, this is a little funny, right? I mean, notice that this is the, like, what three manifold is this the interior of? So it's a three manifold with three genus 2 boundary components, right? Here's a genus 2 boundary component, here's a genus 2 boundary component, and then here's a genus 2 boundary component as well. But somehow, geometrically, one needs to separate this one topological end into these two geometric ends. Right. So, any questions on Brock's thesis? So I should mention that. Okay. So this was Jeff's thesis, but then afterwards he also patched together all these examples here. I mean, by the Nielsen-Thurston classification, I mean, you might imagine that these three examples kind of capture everything that can happen. And so then he finished the picture by by just piecing these together into a general picture of what happens for arbitrary maps F. Okay, so right, general case also Brock. Yeah, you could do, if you want to use the model, you can do things, well, yeah, differently. Yeah. Yeah, I never want to say, like, you can do things really easily from the model, because you always have to extract something from it. but yeah. Mm-hmm. I mean, you get much finer information from the model too. Like, you get what do you get? Well, you sort of, one can analyze, like, exactly how is this length here going to infinity? Well, you really see that it's, the length is increasing linearly with I and stuff like that. So, yeah. So, yes, maybe we can transition now to talking about iteration on Schottky space. So maybe just to motivate it. Well, all right, so this was a nice example. So iteration on when we set our M to be a surface across an interval. But okay, so if I have any M, and I take one of its boundary components, so if S is a boundary component of of some general M, then I can look at the pi 1 of S cover of M, and what I get is a compression body. Okay, so all right, what is a compression body? Well, so there are two sort of extremes to compression bodies. So, examples. S cross 0, 1 is a compression body. Okay, and so how do you get this as a cover? Well, you get this as your cover if the inclusion of pi 1 of S is injective. Okay, so if pi 1 of S injects into pi 1 of M, then I get S cross 0, 1. So. Well, I guess I should. What's that?
What is the pi 1 S?
Just take the subgroup of the fundamental group corresponding to. Take the pi 1 of S as a subgroup of the fundamental group. Say again? Well, yeah, but then I can take the cover of M that has that fundamental group. Well, I mean, it may not be pi 1 of S. I'm taking, like, the image of pi 1 of S in pi 1 of M, and then. Yeah, right. So, Right. Okay. Maybe to just to emphasize this, I should say like the I star of pi 1 of s cover of M. Okay. And so if I star is injective, then this cover is across. I guess I should. I need to allow. I'm confusing M with its interior here a little bit. So. Okay, so let's take the cover of interior of M here, and then let me write S cross R. Okay, and so this is one example, and then on the other for the other extreme, we also have a handle body, which is like a solid surface. Okay. And so, right, so this would, so for instance, if you take a handle body and then you take the cover of the corresponding to the boundary, well, it's the handle body again, right? So, yeah, and then sort of intermediating between or interpolating between the surface cross R and the handle body are things like, well, I could take a surface and then I could fill in the left half. And then have like a torus interior boundary component here. Okay. And so all these are these are compression bodies, but right. And so all I'm trying to convince you of here is that somehow. Maybe I won't make any attempt to justify the following statement more than by writing on the board. But so in some sense, all the interesting geometric limits should be available when either M is a surface cross an interval, or a handle body. Okay, because somehow every interesting geometric limit that you get in the compression body setting, you sort of already see in the handle body setting. And so really, and then you might wonder about general M. Well, and so if you have convex co-compact structures on a general M, then you can lift them to convex co-compact structures on these compression bodies, and I'm saying sort of very vaguely that any sort of interesting degenerations you see should already be available in the interval bundle or the handle body setting. Okay. So hopefully this motivates then me talking about the handle body for the rest of the time. All right. So the rest of the lecture is called iteration on Schottky space. Okay, so Schottky space here just means QH of a handle body. So, right. So with Cyril Lequire, so what we do is we characterize all geometric limits of sequences Q of f to the I of x, where x is a point in the Teichmuller space of the boundary of our handle body H, and f is a homeomorphism of the boundary. And so we'll see. I mean, I probably won't. Well, maybe I'll end up stating, sort of stating the theorem. But I think the statement's kind of complicated, and so I think it'd be more interesting if we just first at least talk about some examples or some differences between this and the iteration in a bare slice. So differences with iteration in a bare slice. So, okay, well, maybe the first observation is that when you're iterating in a bare slice, you could really read off the topology of the geometric limits from like the Nielsen-Thurston type of the map. Okay, so if I had a partial pseudo-Anosov, then you saw that in the geometric limit we were just slicing out the support of the partial pseudo-Anosov. And so in this case, the Nielsen-Thurston type is sort of irrelevant. So the Nielsen-Thurston type of F doesn't matter. And so how do you see this? Well, so if, right, so what happens if F, so remember F is a map from the boundary of H to the boundary of H. So if this map of the boundary extends to a map F from H to H, then, well, what happens to our sequence? Well, what you can see is that it's constant. Okay, so then this sequence Q of f to the ix is, geometrically constant. And the reason why is, well, so when you remark the conformal boundary by f, okay, so when you act by f on the conformal boundary, if this extends to a map from H to H, then really all you're doing is remarking the entire manifold. Okay, right. So we just remark H at each step. And so geometrically, you're not changing the geometry of the manifold. You're just changing the way that you're looking at it. And so geometrically, we have a constant sequence. Okay, and so right, and so what that tells you is that so you can come up with a f that extend to the handle body of whatever Nielsen-Thurston type you want. For instance, so if alpha and beta are two meridians on boundary H that fill, then the twists around the meridians extend, and then the twist around alpha composed with the inverse twist around beta is a pseudo-Anosov that extends. Okay, so you have pseudo-Anosov maps that give you geometrically constant sequences. Okay, so all is not lost. In fact, so the Nielsen-Thurston type of something is still relevant. And so what's the point? Well, so it turns out that, okay, so maybe there are these extension issues, but so it turns out that, so there exists a maximal subcompression body. So it's a compression body that sits inside of H with the same exterior boundary. a power of f extends. So the picture is somehow now that, all right, here's your here's the boundary of your handle body, and then this subcompression body looks maybe like something with these two genus 2 boundary components, and then there's the rest of the handle body underneath. And so if you act here by f, let's put this in parentheses, then f gives you an action down here on the interior boundary components. So f, if I'm saying that f extends to this subcompression body, then it also acts on the interior boundary components. And it's the Nielsen-Thurston type of the maps down here that are relevant. Okay. All right. So, okay, so in some sense, yeah, so the Nielsen-Thurston type of f itself doesn't matter, but really it's just because there are some other maps where the Nielsen-Thurston type is relevant. Okay, but there are a lot more problems too. So maybe another example. I think the way that I'm stating it, this example is actually covered under the first example, but you can modify it so it's not. Okay. So let me take this, this is my handle body. And now look at this curve. Okay. So in the handle body, note this is not primitive in the fundamental group, right? It's a double of this core curve. Okay. So what happens if we twist around this? So if this is gamma, then so what's the limit of q of twist around gamma to the I of x. All right. Well, if you remember your Kirchhoff-Thurston examples, then you might think, well, I should just push this gamma slightly into the handle body, and then I should drill it out. Okay, that can't be the limit. Why can that not be the limit? Well, okay, so let's see what happens if we push this in and drill. Well, this is not hyperbolic, because you notice that I can take this torus here. So this torus is it's an essential torus that's not boundary parallel. Okay. Okay. So the limit can't possibly be obtained by pushing in gamma slightly and drilling it out. And so what do you think you get? So here, the limit is actually obtained by drilling the sort of core curve that's the primitive root of this curve here. So now okay. And this is actually not so hard to verify. I mean, essentially, once you know that you're going to be drilling out a curve, then you sort of can imagine that that these manifolds are obtained by Dane filling this manifold with a cusp. And so once you guess that, then you can just verify that indeed they have the fillings of this have the correct conformal boundary. Okay.
Do
You guys have thinking about the central torus and just the hyperbolic piece of the JSG on the outside of it, and that torus is getting further and further away geometrically.
See what? See the fact that you realize this at the limit?
Drill that curve, because drilling out that curve is the same thing as drilling out the interior of your green solid torus.
Well, I mean, I think that, as I said, the way that I would see it is via this via the Dane filling argument. I mean, you just have to say that, you know, if I start doing these Dane fillings, then you need to recognize what conformal boundaries do you get, you know, with the appropriate marking, and you get exactly these conformal boundaries, and so that tells you that, you know, by the Dane filling theorem, that these are converging to that one. Yeah.
Is it clear that it's only one bit?
Yeah, it's not clear, and in fact, I mean, here, you know, here essentially there's one limit, and in fact, but in other cases, yeah, there may be there doesn't have to be a single limit. Like depending on where the base points are, you can get different limits. I mean, we saw that already in the iteration in the bare slice. You know, like when you're doing the pseudo-Anosov example, if you put the base point here versus here, you get different limits. Yeah. So yeah, and maybe okay. So just wanted to end. I'll just mention one other interesting example. So, yeah, I mean, really, most of the examples of strange behavior coming from, you know, iterations in Schottky space come from looking at a handle body as an interval bundle over a surface with a boundary component. Okay, so H you can regard as you take a surface T with a boundary component, and then you take T cross I, so T cross 0, 1. And so, all right, let's put more genus on so I have some room to move here. And so then you could ask things like, well, okay, say I take, I do some map with a boundary that's a pseudo-Anosov here, and then I do some other pseudo-Anosov down here. Then, okay, so what happens? You might want to say that you cut out something in the limit, but sort of for similar reasons as we saw over here, you can't be cutting out like this surface pushed in and this surface pushed in. Essentially because you'll be developing two homotopic cusps. And so what happens is that in this case, okay, you might think that you push like the part that you're doing a pseudo-Anosov on, which is these two pieces in, and you drill them out. But in fact, you don't. You drill out. So in the limit, you end up so drilling out just one copy of the surface. So the fact that these surfaces are homotopic in the handle body means that there's some interaction that you're forced to compensate for in the geometric limit. Okay, so I think I'll stop there.